In this lecture, we're going to look at a recent and real-world and commercial as well application of the seismic imaging, seismic reflection technology we've been talking about. It's a further development of that technology, way beyond the kinds of analysis that I've been showing you, but it does illustrate for you the kinds of things that one needs to do to get real world solutions of economic problems that we have, such as in Nevada. So this is an extended lecture on advanced seismic imaging for geothermal development, as applied mostly by my former students, Satish Pulmanopoulil and Bill Honges, who are the technology vice president and the president of Optim Inc., which is a technology startup company started right here at the university and still located here in Reno. And you can get more details about what I'll talk about at the website down below that you're used to looking at, and also at Optim's website, and now also at kbgeopower.com. Klamath Basin Geopower, kbgeopower.com. So one thing that I need to lay out first is the difference between two different kinds of geophysical methods. One way of dividing geophysical methods is into integrative versus differential. And methods like, as you'll find out, gravity, magnetics, magnetotellurics, and I think you've probably got some idea that refraction and also refraction microtremor, they integrate over volumes. And so we lose resolution rather quickly as we look below the surface and below the places where we have our sensors set up. Those are seeing as they integrate over volumes, we call them integrative techniques. There are just a couple of techniques that are not integrative, that image point changes, okay? And those are seismic reflection is the one that's most popular, and also ground probing radar, okay? So what we're going to see here is an application first of integrative methods to geothermal exploration, which is then going to enable the proper use of seismic reflection, a differential method that's able to pinpoint the location of geothermal reservoirs. Now, you've probably heard that seismic exploration has been seismic reflection exploration in particular has been a cornerstone of oil and gas exploration and development. But until the last 10 years, it wasn't used for geothermal projects. Okay, now why was that? A lot of lateral complexity of the Earth prevented accurate modeling of velocities, and then in turn, the lack of accurate velocity information and models prevented focusing of the reflection data. And without well-focused reflection images, we didn't have seismic images that we could actually interpret. And so, without an adequate seismic image that's interpretable, then there's no added value in doing the seismic reflection work. So for a few decades, while the oil industry was pushing ahead and making a lot of progress and finding billions, maybe trillions of dollars worth of resources with seismic reflection as the main exploration technique, the geothermal industry was deprived of these very basic needs and was unable to, find an economical but accurate method of mapping the subsurface. So this resulted, even to this day, that too much geothermal exploration is being done with a drill bit. And as you know, that's the riskiest and the most expensive way to do exploration. So the solution to this problem is to solve the velocity problem. All right, and there's a technique called simulated annealing velocity optimization. You have already seen it in terms of the code that Satish ran your picks from Lab 1 through, and you've all seen now the results from that code. And so this simulated annealing velocity optimization, commercially known as SeisOpt at 2D, was the result of research in the Seismolab here in the early 90s, particularly Satish's thesis. And then in 1998, after some development work, Optum was able to release it commercially under the name SeisOpt, which they registered as a trademark. So SeisOpt iterates through hundreds of thousands of possible velocity solutions to find a global solution that best fits the seismic data. And it doesn't have to assume any direction or magnitude of the velocity gradient. So, very radically, velocity models with radical velocity changes, pretty accurate representations of some of the fairly heterogeneous geology that we have here in Nevada. And also, velocity does not have to increase with depth. It can increase more laterally than it does with depth. So that's what we're saying about, assuming no particular direction of the velocity gradient. We're not assuming that velocity only increases down. So, Optum and I have put together what we call advanced seismic technology and applied it to a number of geothermal developments. We've proven the effectiveness of SeisOpt velocity optimization techniques. We did pilot studies in Dixie Valley and Coso, which is a geothermal area in eastern California. And these are on both magmatic and extensional geothermal systems. You may know that geothermal systems can be divided into those two different kinds of sources of heat. Now, the success of these early applications led us to design seismic surveys, that used new sets of seismic acquisition parameters. And these new parameters enhance the results from the advanced processing techniques. So it's not just processing, it also counts a lot how you record the data. So then, given the accurate velocities from SeisOpt, then we bring in another tool called pre-stack Kirchhoff migration, often known as pre-stack depth migration, or you might even see it abbreviated as PSDM. And that's able to take advantage of the velocity information, characterize significant features in the subsurface, and especially the ones that have to do with permeability in the geothermal reservoir. And also, we can look, down dip from features that are mapped to the surface and get their geometry in the subsurface. And one of the things that we've been able to do is image tectonic structures and determine the relationship of stratigraphy to faults, fractures, and other controls on geothermal reservoir permeability and production. So let's take a look at these two advanced processing techniques. Okay, so the nonlinear velocity optimization, via simulated annealing, it produces high-resolution velocity models from first arrival picks, right? Which just like you made off raw shot gathers, and this is it's seismic refraction data, just with the most complete possible interpretation, and thus it's integrative. Okay. Then the pre-stat Kirchhoff depth migration, which directly images subsurface structures. They can be oriented in any direction. That's the differential technique. Okay, seismic reflection. There's several advantages to this pre-stat Kirchhoff migration. It turns out that a lot of the pre-processing, the filtering, the amplitude equalization, removal of other kinds of waves, a lot of that has to be done by hand, and is quite expensive and time consuming. Time is money, especially when things are being done by hand. So it turns out that the pre-stat Kirchhoff migration, way more than stacking, way more than time migration, PSTM, PSDM, with Kirchhoff, the Kirchhoff technique, really only demands minimal pre-processing. There's a lot of pre-processing steps that are common to more conventional seismic data processing used in places that are not as heterogeneous and where you don't need as good a velocity model. And there's a lot of man hours, person hours put into these pre-processing steps. And sometimes what the pre-processing does is, as we found by some less experienced seismic processors that have been trying to operate in Nevada, sometimes there's quite a penalty to be paid. They've in the pre-processing they actually remove some of the useful data that we'd rather have go directly into the image. Another advantage of this pre-stat Kirchhoff migration, we directly image the structures to depth. We don't go through this intermediate time section model, and then where we do stacking, we do migration. That's all in time, and then we finally do a depth conversion to convert from time to depth. We go directly to a cross section in depth. So and we can do that because we have the accurate velocity models, and we can place the reflectors at their correct location, at their correct depth. So we're the standard conventional time to depth conversion, we can avoid it. It's unreliable. We don't need it. Also, stacking is best suited to simple conventional seismic processing. It's best suited to imaging flat dipping structures. Okay, and only those. The dipping ones, it can't, especially the steeply dipping ones. Stacking, even followed by migration, really can't handle. Okay, and especially where flat structures intersect with dipping structures. Stacking just cannot resolve both at the same place, okay, at the intersection. And those intersections are very important spots within our reservoirs quite often. So Kirchhoff migration can image structures oriented in any direction and intersecting structures oriented in all directions. It can handle velocity variations in any direction. It can image flat dipping structures, moderate dipping structures, and steeply dipping structures. It's really ideal for imaging in areas with extensive faulting and frac. So now, the upshot of all this is that with the size opt analysis, we can we can actually increase the feasibility of geothermal projects. All right, so some of our earlier work involved creating volumetric depth models of Earth structure, and they can be quite extensive. In one case, 11 square miles to a depth of 15,000 feet, and all that cost less than half as much as a single exploration drill hole. All right, so these volumetric size-up models, the integrative part, we can use them to reduce directly, even before the Kirchhoff imaging. We can still use them to reduce the risk and increase the productivity in all three phases of geothermal development: exploration, production, and the management of the reservoir. So I'm going to show you several case studies. We're going to look at Dixie Valley, just a couple hours east of here. It's a case study of production and resource management. The field was discovered and developed some years before. And it's also a case of taking advantage of the integrative nature of size-off results. The Coso geothermal field in Inyo County, California, Eastern California. That's another, there's some exploration aspect to this and also resource management, still integrative, okay? Then we'll move to the differential cases. We'll look at some spectacular reflection images from Pumpernickel Valley, which is central North Nevada, between Winnemucca and Battle Mountain, or really, southeast of Winnemucca. And that's an exploration prospect and a differential image. And then Astor Pass, Pyramid Lake, right here in western Nevada. That's another exploration project and some spectacular differential images. So in Dixie Valley, the objective was to improve an existing field by understanding the geothermal system better and the tectonic structure. In this map, we see a number of production wells and injection wells, and also seismic lines that were shot back in the 80s. Okay, some of them are more or less in the strike direction. Many of them are in the dip direction. And so back in the 90s, we reprocessed these lines using size-up technology. And here's an example of an optimized velocity model. It might look rather similar to some of the models you've seen from your Lab 1 work. Now, I should go back and explain. This part of of Dixie Valley is way to the north of the shallow dipping Dixie Valley fault that you were looking at in Lab 1. That's in southern Dixie Valley, and this is about 60 kilometers north of there in northern Dixie Valley. That's where the geothermal plant is, and all these wells. So there are variations of a factor of 2 or more in velocity laterally over relatively short distances here. Of course, there's also variations in velocity that are vertical, and velocity does generally increase with depth, but the lateral variations are even out here in the middle of the basin are something that we had to get control of. And so by creating size-opt velocity models of all these different lines, we could put them together and interpolate velocities into a 3D volume in between the lines. And what we saw are these basin-ward synforms, here with lower velocities to deeper depths. Okay, and the location of those synforms corroborated with gravity data. Okay, so and also corroborated with the locations of production and injection wells. We could see all varieties of these synforms. So here's this cube that shows on this face the one of these synforms and the locations of some of the production and injection wells. So here's a now taking this into the differential mode, okay, and actually doing that pre-stack Kirchhoff depth migration. All right, we can see the synform in the reflections now that we've got the velocities properly taken care of, and that's accurate now. And we can see there's no way that the range-front fault comes from the surface and gets down to the bottom of this well. What we're looking at is a buried, more ancient fault. It's still a normal fault, and it's still east dipping, just like the range-front fault, same direction. East is on the right here. But as you can see, some mid-tertiary sediments basically cut off this fault, and it didn't rupture after that time. So the synform, was a piece of earlier basin development, which you can see the sag did kind of persist for a little bit, and it's these basin-ward faults in Dixie Valley that we first noticed as really providing the sites for the best injection wells and the most productive production wells. So here's a look at the gravity contour map, and you can see that there's there are these faults that are located with the seismic analysis, and there are faults that are located via these gravity gradients. The places where the gravity contours are a little bit tighter, and we find suddenly that all the most productive wells are located not on the steeply dipping range-front fault, which is up here to the northwest, but on these basin-ward step faults. Okay, out here further to the southwest. So, and these gravity interpretations are completely independent and done, in fact, by Dave Blackwell at SMU, noted geothermal scientist. So, we have here an excellent correspondence between, the well data, the gravity data, and the seismic data, both the velocities and the differential reflections. So, kind of putting it all together, here's a section which shows it's got the velocities, underneath in color, and then in black and white on top of it is plotted the reflections. The top of the tertiary volcanics is a strong reflector in many of these basins that we can notice, and we can also locate better the range-front fault, but the basin-ward step fault is a bit steeper, and that's what's creating the synform, and the well is actually going into that basin-ward fault and not into the range-front fault. And this contrasts against a model that was proposed by Okaya and Thompson a long time ago, from the same data sets, but not properly migrated. And they really had the range-front fault at a much shallower dip, and proposed that the wells were intersecting the more shallowly dipping range-front fault. Now that would match the shallower dip of that we see down in southern Dixie Valley, but up here in northern Dixie Valley, it turns out to be a little bit too quick of an assumption that we would see the same dips of faults 60 kilometers away. And in fact, the whole tectonic system is different in northern Dixie Valley than southern Dixie Valley. So that's what has generated the difference in the faults that are productive. So in Dixie Valley, a previously unknown basin-ward half graben, we located with seismic data, and that correlates with production and injection wells within the geothermal field there. The half graben got incorporated by the operators of the geothermal field into their injection and production model, and then they did some well tracer tests, where they inject fluorescein dye or other tracers, and they confirmed that those basin-ward half grabens and sags, were higher permeability, and that was the path where the tracers actually took. So that seismic survey and the advanced seismic processing of it really settled this a very basic controversy, over whether you should locate production injection wells along the Dixie Valley Fault, the rangefront fault, or whether all that was controlled by basin-ward structures, and it was controlled by basin-ward structures. And so before the seismic data, the true source of production wasn't known. Okay, and we needed the advanced seismic data to reveal that. Now, just a note, this is an oblique Google Earth view of Dixie Valley. So we have the low angle fault down here at Willow Springs and Cattle Road and Little Box Canyon, Big Box Canyon, where I worked on it back in 1998, and wrote that up in a 2001 paper, I think, by Rob Abbott. And these red traces are the 1954 historic rupture of the fault. And here's those shallow thrusts in the muds that got worked on by one of Bob Waters' PhD students. And so we do have a low angle fault, but it has a northward dip, and then 60 kilometers to the north, where the fault now in yellow, it's not a historic rupture, really has a northeast dip. That's where the geothermal field is, right up here. And it's not a low angle fault. It's a 70-degree dipping normal fault. So this can all explain our observations. There's no the geothermal resources way up here on the north end of the fault. It's not on the south part of the fault. And why is that? The low angle fault does not tap into the deep parts of the crust. It's too shallow angle. And that's why it's not bringing up heat from below, and certainly not enough to make a geothermal field. So here's our low-angle image using the data set that you have taken a look at in Lab 1 and in fact a bit in Lab 2. And it's reflection stack and both at very very high resolution in this little end setup here, and at kind of basin scale resolution down here. Constraints from gravity on where the basin goes, and we see good correspondence between all that and a 30-degree dip on very shallow dip in southern Dixie Valley on the Dixie Valley Fault. So no basin-ward faults here. Okay, let's move to the Coso geothermal field in eastern California. Okay, one of the more productive geothermal areas in California. So we're out here just east of the Southern Sierras. And we're looking at a magmatic geothermal area. Lots of relatively recent cinder cones. Okay, and the study area is up here in the Coso Hills, and that's where the geothermal resource is. Faulted quaternary volcanics are what we're looking at. And here's a map in the upper right of one line out of many that are spanning this area. This line is about 6 miles long, and the hotter colors are higher velocities, and we can see between the red and pinks, very high velocities. There's this area in the middle, which corresponds to the reservoir area that's been productive for about 20 years in terms of geothermal resources, we can see lower velocities within the reservoir area. Okay, green is really lower near surface velocities, and you can even see a fault in here. All right, so same process. We make a volumetric model from the 2.5 dimensional data, right? It's a network of 2D lines. We interpolate between the velocities that are along the individual 2D lines, and that reveals for us the 3D geometry of the features. And so we can slice our way down through that, and you get, for instance, to 4,000 foot depth, and the reservoir area, in green and in low velocity, becomes very obvious. Surrounded by higher orange and red, higher velocity orange and reds. Okay. Also here at 3,500 feet, there's this other area at the Coso Wash, which is also a low velocity area. Now, what's the significance of low velocity geothermal? It's more faulting, more fracturing, more comminution and dissembling of the rock, and the lower the velocity is, right? The fracturing, the faulting is reducing the, greatly reducing the strength of the rock, the elastic moduli. And just like in Dixie Valley, then we make an image of pre-stack depth migration. This is really very deep. We're looking down 15,000 feet here, okay, and more, 20,000 feet. We can see very hot brines coming up from far down below. We can get a sense of some of the major faulting, the Coso Wash fault in red, which we actually can see imaged as a fault plane in the images. We can see these other structures in here, and then a kind of a master detachment fault that underlies the whole field. Okay, so we've been able to define in Coso discrete thermal reservoir areas. So there's two distinct reservoirs within a volcanic pile. We can see the brittle ductile transition, way down below, 20,000 feet down. We've predicted the orientation and location of fracture systems, and there's also this deep bright lens reflector. That's the one at 20,000 feet. The brittle ductile transition is a little bit higher up in this high temperature area, and it's probably high temperature brines that are providing that bright lens reflector. And we couldn't image that at all without getting that accurate velocity information up above. So after these early projects in the 90s, we could conclude that seismic exploration can reduce the risk and increase the productivity in all phases of geothermal development: exploration, production, and resource management. Seismic exploration is is not only effective, but it is economic. It is feasible. Okay, it's giving now, with the SeisOp technique, significant added value, and it's cost effective. We can make these volumetric models encompassing many square miles, right, and extending to great depths for much less than it costs to drill a single hole. And really, seismic exploration is the only geophysical method that can directly sample the subsurface to depths exceeding 8,000 feet. So we can use it to calibrate and corroborate MT and gravity data. Provide the, in some sense, the ground truth that you lack when you model the integrative magnetotelluric and gravity data sets. Let's move on to a spectacular differential example, Pumpernickel Valley, central northern Nevada. Here's a topo map of the area showing with the blue numbers the seismic lines. There's, I think, 5 seismic lines, 6 seismic lines cutting through this area in various directions. So it's a small network. You can see the sections. Each line is a few miles long. It's a small network of 2D seismic lines. Okay, not a 3D survey. There's dip lines and tie lines. Here's a raw record, and the airwave is pretty clear. You can see the first arrivals. They're nicely clear. So picking the first arrivals is not a problem. And then there's all these sort of wormy reflections. Okay, they're pretty strong. They're pretty continuous, but not all the way back to zero offset. And certainly, they're not showing their minimum time at zero offset the way they ought to. So the reflections are all over the place, and it's a real mess. Okay, so but we had no problem picking the first arrivals, and we can get the size opt velocity sections like for this particular line, number 3, and showing lots of lateral heterogeneity. Factors of 2 velocity increase over relatively short distances. And we can use that velocity map to migrate even below the velocity map, and we start to see these steeply dipping structures as reflectors. Okay, we can see shallow dipping structure. We can see the intersections between shallow dipping structure and steeply dipping structure. We can see stratigraphy in the alluvial fans. So the picture is starting to come together, the stratigraphy and the structure. It's especially interesting to put the velocity results together with the reflection results, like here. And so in red, we can trace out the range front fault. It's quite a strong reflection itself, down to a significant depth. But there's also these other faults that appear as like this yellow one, and they're completely underneath the basin. Right, here's the bottom of the basin right here. Here's a fault that's bounding a half graben on the earlier subbasin. Okay, and both of those faults, the yellow and the blue, are sealed off by later sediments. So they haven't been active recently the way the range front fault has. And this is line 4, which in this case the range front fault is clear. We can see it and identify it, but it goes right up to its outcrop at the top of the section. But the strongest fault reflection is not from the range front fault. It's from one of these basin-ward step faults. And this one has a very strong reflection on it. And it's also associated with very stiff lateral velocity variations. Green to pink here is about a factor of 2, over these really short distances. Well, let's see, I'll go back. Beautiful image here of the stratigraphy within an alluvial fan, another thing that's quite rare. And now here again is the same blue fault, which is starting to merge in with the range front fault. And other faults are appearing. There's a whole system, a whole network of basin-ward normal faults. These are synthetic faults. They're not antithetic. So looking at these 3 sections, line 3, line 4, line 5, you can start to get a picture of what reflections are quite important, and the different orientations of the different faults and the different ages and depth extents. And the only one that's manifested at the surface is the range front fault, the red one. All the other ones are completely hidden and blind. All right, and this this is actually yet to be drilled, but there's got to be something to the high amplitudes here in line 4 in the center. The high amplitudes associated with that steeply dipping fault plane, and so you can trace out the faults just by on each line, marking and connecting the faults. So this blue one, which is the most reflective, is kind of northeast striking, north-northeast striking for the range front fault in the same area, and then other faults crossing through. Okay. Now we suspect that the blue fault is the source of the geothermal reservoir because the hot springs are above that one. They're not above the rangefront fault. So in Pumpernickel Valley, we've done a specialized seismic survey. It's very well imaged a hidden basin-ward step fault, and it's imaged it as a fault, as a seismic reflector. So we can start to examine faults and the reservoirs they contain in the same way that the oil industry has begun to has for years been examining stratigraphic reflections. Okay. So in Pumpernickel, the network of 2D lines explore the prospect at a fraction of the cost of 3D. The acquisition in this case was specially designed for the best size-opt velocity results. And the good velocity info allowed imaging faults in alluvial stratigraphy as well. And Nevada Geothermal Power still wants to drill this prospect, but how soon will they be able to do it? We're not sure. So now for a final example, let's look at my most recent work on the Pyramid Lake Pyote Reservation off the north end of Pyramid Lake itself, at a place called Astor Pass, which is kind of between Pyramid Lake and the Honey Lake Valley. And this is a piece of exploration using differential techniques. We did again our own specially designed and network of 16 two-dimensional lines. So I call that 2D wide azimuth, 2D WAS. All right. The lines were 2 to 7 kilometers long. The source receiver spacing was 17 to 67 meters. We were aiming at looking at the upper 2 kilometers of the section, and there was a 10 to 25 meter vertical resolution. Okay, and using up to 240 channels on the receiver lines. And this is sponsored by Department of Energy and the Bureau of Indian Affairs, but our contract to UNR that we're still working on here came from the Pyramid Lake Pyote tribe, and we very much appreciate their support and as well as their collaboration in this project. So on the right is the standard processing, which, as you can see, really only succeeded in showing the bottom of the top of the volcanics, the bottom of the quaternary sediment. This is on a relatively short line, and the basin is relatively narrow here in Astor Pass. On the left, we have Satish's processing with Optim. It's showing the top of the volcanics as it should, but also it's showing a very strong, very coherent reflection from a steeply east-dipping fault. There's also a little bit less coherent, but still pretty strong reflections from steeply west-dipping faults. Okay, so we're directly imaging the faults on either side of the valley, which is giving us a lot more power to figure out what's going on here tectonically and geothermally than the standard processing had before. And having these steeply dipping reflections buried under volcanic flows, below the top of the volcanics, that really made it a very difficult prospect. But SizeOpt can handle it. So here's putting a few lines together into a 3D view in this open source software called OpenDetect, which is a really very capable 3D seismic interpretation system. And you can see here's that. It's kind of a southward view here. So this is the eastward dipping fault at A, and we interpreted that. And there's as you can see, we've interpreted many other faults within the data. And then we drilled it, and within a well called APS3, Astor Pass Slim Hole number 3, at a depth of 1,300 meters, the geologist noticed a fault gouge or a broken up fault type rock, and that fault gouge in the well turned out to be within 27 meters of our seismic interpretation of a fault. Based on these reflections, fault reflections we can see directly, and also offsets that we use to offsets of stratigraphy that we use to draw in faults as well. So we made a prediction before the drilling of where the fault was, and then after drilling, we saw that we were within 27 meters of where the drill hole intersected an actual fault. We also managed to image the volcanic stratigraphy. This is a view of a couple of the other lines, and now we're kind of a north-looking view. So in this line here, the volcanic stratigraphy is very strong. We're not seeing the top of the volcanics that well because it's just a rather fractured rhyolite. But in this area right in the center, there's a very clear demarcation between a reflective sequence of basalts with interbedded sediments and a rhyolite dome that overlies it. So the rhyolite domes have these less reflective interiors, as we're seeing here in the center, and we have the strong reflectivity of tertiary basalts. We picked the top of the tertiary basalts, and then this same well APS3, which is actually at the intersection of these two lines. Okay, that well, penetrated the rhyolite dome to basalt transition at a depth of about 600 meters that we had picked from the seismic with 10-meter accuracy. Okay, so the seismic imaging, especially when we can design the experiments ourselves, is becoming very successful at locating features, structures and stratigraphy, even in these very complex and heterogeneous volcanic piles. So the seismic survey at Astor Pass discovered new fault sets entirely. That we didn't get uniform quality of fault plane images. It depends on the survey orientation, and we're working on 3D imaging. The excellent imaging of the tertiary volcanic stratigraphy, we really, domes versus flows, we didn't expect to be able to see that. And we verified the volcanic stratigraphy. We verified the faults with newly drilled wells, so it counts as a confirmation, okay, as a blind test. And fault imaging, now that we've imaged these faults as direct seismic reflections, we can start thinking about analysis of geothermal reservoirs in the same way the oil industry thinks about analysis of oil reservoirs. Okay, we can use techniques such as seismic attributes and AVO, which is short for amplitude versus offset. These are all ways of analyzing reflections and trying to tie them into known stratigraphy and physical properties. Here's another example. It's from an Optum project at the Oregon Institute of Technology in Klamath Falls, Southern Oregon. We can see direct fault plane images in several places, and they drilled the well to intersect this fault and then run along the fault. And the drilling intersected the fault within 15 meters of where the seismic interpretation said it would. Very, very close. And that was at a depth of 3,500 feet. So, not near the surface at all. Very difficult to get that kind of accurate interpretation. The new well provides enough heat to meet 60% of the electrical needs of the OIT campus. So really a good economic success here, and this is kind of presage the work that Optum is continuing as Klamath Basin Geopower in the Olean Gap area. So again, I can't emphasize enough how important it is that now that we have direct fault images in seismic reflection, we can look at seismic attributes, instantaneous amplitude, instantaneous phase, instantaneous frequency. We can look for edges, shadows, coherency. All those favorite seismic attributes are now available to us on faults, not just nearly flat stratigraphy. We can look at these fault reflections for their amplitude versus offset, and that tells us something about the Poisson's ratio on the fault, and maybe will tell us something about the porosity and permeability of the fault. Also, we can look at amplitude versus azimuth (AVA), and that should tell us something about fracture orientation. Okay, which is going to get us into some data on the mechanics of the reservoir, which being a fractured reservoir, that's very, very important. And we can even start to think about seismic inversion. We want to take the reflectivity that we're seeing on these faults, and we want to try to separate. What does the fault mean in terms of a density contrast, delta rho? What does it mean in terms of a Lemay lambda parameter contrast? That's an elastic parameter, delta lambda. What does it mean in terms of a rigidity contrast, delta mu? So all of these we can now start to analyze, and my grad students are starting on that path. So that's not all. There's some successes that I can't show you the details of, but in 2011 at Hudson Ranch in the Imperial Valley of California, that's southeastern California, 5 of 5 wells that were drilled, guided by seismic, were economic. Okay, so we're starting to look at an era when we don't need to do exploration with the drill bit anymore, and that's going to be a lot more efficient and is going to raise the economic viability of geothermal prospects. Now we can, now that we can do direct imaging of the fault reservoirs that the geothermal fluids sit in, we can start to search for the geothermal seismic signature, with these attributes, with this AVA, with this AVO. And much appreciate your attention. This is a been a lecture on the real world application of seismic reflection for energy resources right here in Nevada.